Good morning, students. Mr. Eck here. Today, I'm here to talk to you about radians. Radians are a unit of angle measure that is actually more intuitive than degrees. And people think radians are hard, but I'm here to tell you that if you can cut a pizza or eat a pizza, and you're not one of these weird people that cuts your pizza on a grid, you can do radians as well. This is a hands-on activity, so today you're going to need two circles of roughly equal size. I traced my coffee mug. You can trace anything you want. The bigger the better. You'll need some scissors, and you'll need some things to write on. This can be scratch paper. I use the back of a math team test. So radians are a measure of angle that is superior to degrees because they are linked intrinsically to the circliness of a circle. Degrees add up to 360 around a circle, specifically for no good reason. It dates all the way back to the ancient Babylonians, who had a different number-based system, and 360 worked really well for them. It is, last I checked, about 4,000 years later. We can probably do better. So what is the basis of radian measure? Well, the basis of radian measure is a unit circle. That is a circle of radius 1. And we know that in this circle of radius 1, the circumference is given by the formula 2 pi r. So then the circumference all the way around the circle, excuse my terrible drawing, would be considered 2 pi units of circumference. Well, we're also going to define a radian angle as the central angle that matches with this entire arc. So for a circle of radius 1 and an arc of the full circumference, which is 2 pi units, we're going to say that that is the angle measure equivalent of 2 pi radians. So in a sense, 2 pi radians is equivalent to what we used to think of as 360 degrees. That said, I'm going to try to not use the word degrees throughout this video, and we're going to start thinking and working only in radians as fractions of circumferences of circles. This is the interactive part of the video. I would like you to take your first circle and slice it up as I've diagrammed below. So you're going to cut it in half, then take half of that and cut it in half, and then take half of that and cut it in half until you have 4 pieces of differing sizes as shown. Pause the video now and do this. I hope you have your pieces. I have mine. They're really hard to see on camera. And I want you to first pick up your half circle. We're going to define the radian measure of that half circle. Remember that a full trip around the circle was 2 pi radians. So a half trip around the circle, that is the central angle given by a half circle, will be 2 pi over 2, or pi radians. And on your little, it's hard for me to draw on the tablet and on paper. On your little paper piece, which I've simulated over here in green, I'd like you to mark the center, draw the central angle, and mark this as pi radians. By the way, the unit for radians, you don't actually need to write anything. If there's no unit symbol, it's assumed to be a radian angle, so it's okay to just write pi. If you did want to write a unit, you can write rad, which is short for radians. So now I want you to take the quarter circle and think about where that came from. You had a half circle, and then you cut it in half again. So we can think about that central angle as measuring a total of pi over 2 radians. And that's what I'd like you to do on your little quarter circle piece, is label the center, mark the central angle, and label that central angle as pi over 2 radians. I guess I am going to write, I said I wasn't thinking in degrees. I will write the degree equivalence over here also. So pi was approximately, well, not approximately, in degrees was equivalent to 180 degrees. Pi over 2 then is our equivalent of 90 degrees. And I bet you can guess what's coming. Think about when you made those two smallest pieces. You had taken a pi over 2 and you cut it in half. So each of these pieces is going to be pi over 2, which is equivalent to pi over 4. And I'd like you to take your little smallest piece here, label it as, mark the central angle, label this as pi over 4. And the degree equivalent of pi over 4 radians is 45 degrees. These are some of the most basic and fundamental radian angle measures. There are, of course, ways to convert between degrees and radians, but honestly, these are the ones that are some of the ones that you're just going to want to know, and you will build that through memorization, and you'll also build it through practice. We learn radians best just basically by immersion, in the same way you learn a foreign language. So not by converting to degrees every time, but just by thinking in radians all day, every day, as we do problems. We will summarize all this at the end, but I have one more task for you. I want you to take the other circle, and you're going to cut it a little more in a more difficult way. You're going to cut it in half first. Cut the bottom into sixths and the top into thirds. Pause now and do this. Hopefully you have your pieces cut. I have mine. Thirds are harder to cut than halves, so that's a little bit of a challenge. We're going to do the same thing of labeling these pieces as well. We're going to start with the larger pieces. So starting with this half circle, we know that a full half circle is pi radians. So what do we do with our half circle? Well, we cut it into 3 pieces. So that means that each of these pieces will be equivalent to pi over 3 radians. Each of these will be equivalent to pi over 3 radians, and you can label each of those larger pieces as pi over 3. Pi over 3 is equivalent to 180 pi over 3, which is 60. So on your pi over 3 piece, which you've maybe labeled here, maybe on the back or on some other side, or just on your notes, you can make a note that that is equivalent to 60 degrees in degrees. You can now probably guess what we're going to do. We took the same pi radians on the bottom half and cut it into 6 pieces. We could also have cut it into 3 pieces and then cut each of those in half. So each of these will be marked pi over 6. I'm not going to label every single one, but you could. You don't have to label every single one. Label a couple of these as pi over 6. And that's the final kind of fundamental building block of radians, is this smallest piece, pi over 6, that is that is equivalent in degrees to a 30-degree angle. And so now to zoom out and look at the big picture, we have almost all of the basic building blocks of radians. A full circle is 2 pi radians. A half circle is pi radians. A quarter circle is then pi over 2 radians. And a eighth of a full circle is a quarter of a half circle, is pi over 4 radians. A third of a half circle is pi over 3 radians. And a sixth of a half circle, or a 12th of a whole circle, is pi over 6 radians. So you can see now that these are all the kind of famous angles we know in degrees, right? 180, 90, 45, 60, 30. Those are all the most important angles from trig. We've now expressed all of them as fractions of the whole. We didn't have to do anything to do with ancient Babylon now. We have perfect radian measures for all kinds of angles. And you have some nice little toys that you can use to assemble other radian angles, which is what we're going to do next. So say that I was asked to draw the angle 4 pi over 6. I would start with a full circle and recognize that a full circle is 2 pi. Then I would recognize that a half circle is pi. I'm going through this very kind of slowly, baby steps, and eventually this will all go faster. Then I would think about drawing pi over 6. So I would want to be taking this and splitting it into 6 pieces to find those smallest pi over 6 segments. This is the part where I said it's like pizza. And then I'll just count 1 pi over 6, 2 pi over 6, This is 3 pi over 6's, and this is 4 pi over 6. So the angle 4 pi over 6 would look like, in standard position, this right here. 4 pi over 6. It's saying draw 4 slices of pi over 6 size. So think about this as 4 times that basic slice of pi over 6. I wrote below, what other radian angle is this? So one nice feature of radians is to say that I had 4 pi over 6. Well, you can also play numerically with the fractions. That is, 4 pi over 6 is also the same as 4/6 pi, which is also the same, that's a 6, as 2/3 pi, which is also the same as 2 pi over 3. Oh, that makes sense. Let's see, what 2 pi over 3, well, that's the same as 2 pi over 3's. So another way to have drawn this angle, instead of going into sixths, would have been to reduce the fraction. I know that's not quite a perfect circle. Here's pi. Split that into 3's. Here's 1 pi over 3, and this is 2 pi over 3. So 2 pi over 3 and 4 pi over 6 are identical radian angles. They're the same names, or just different names for the same radian angle with a different denominator. So that's a fun thing about radians that you can't do in degrees. And usually we base radians off of pi, but actually 2 pi over 3, you can think about it in another way, which is 2 pi over 3. Well, what would that be? Well, we know a whole circle, ooh, make it a little perfect this time, is 2 pi. So another way to think about this is taking a whole circle and cutting it into 3 pieces. And then this is 2 pi over 3, and then this would be 2 of those, or 4 pi over 3. And then this would be, I guess, 6 pi over 3. Oh, or 2 pi. So that's one of the beauties of fractions, is you can break them up in different ways to locate the radian angle, whatever kind of works and makes sense. But we're all talking about the same angle, which is this pi slice that in degrees we would have just said is 120 degrees. Go ahead and pause the video now and try to draw 5 pi over 4 and 3 pi over 2. Same radians, use the same procedure, use your building blocks to assemble the angle if it helps you, or it helps you look at things. All right. Let's go over the first one. I truly hope you did pause the video. I have no way of knowing that. So 5 pi over 4, again, I'm going to take my circle. I'll split it first into half because that's the pi. And I'm going to recognize that this is 5 times the basic building blocks of pi over 4. So pi over 4 is a half circle split into 4 pieces. So I will split my half circle into 4 pieces. And I'm going to split the bottom half also into 4 pieces because I see that I'm going to need 5 of these pieces. So now I have 8 total pieces, and I'm just going to shade in 1, 2, 3, 4, 5. So the angle that I was told to draw was 5 pi over 4, would end right there in the third quadrant, and the angle itself would be greater than 180. It would be, into that third quadrant. So this is the angle 5 pi over 4. Again, you're just, the denominator tells you the size of your pizza slice. The numerator tells you how many slices you are taking or creating. Same with 3 pi over 2. I chose 3 pi over 2 because that's sort of a famous radian angle, or a very important radian angle. They're all important. This one's extra important. So here, I want to think about this as 3 times the base unit of pi over 2. So pi over 2 would be a half circle, which is pi, and then divided into 2. So this is our pi over 2. Well, here's 1, and I'm going to go just divide the whole circle up then into these pi over 2 bits. Here's 1 pi over 2. Here's 2 pi over 2s. Here is 3 pi over 2s. So you can imagine that we shaded 1, 2, 3 of these quadrants, and the total angle then is drawn like this, 3 pi over 2. And just to give the degree equivalence then, 5 pi over 4 in degrees is 180 plus 45, so that's 225 degrees. Notice how once you have the picture, it's really simple to convert to degrees. If you ever need to, again, I don't encourage converting to degrees in the middle of the problem. That's not very useful. But if you need to convert at the end, you have a good picture of the situation. And same here. We know that 3/4 of a circle is just 270 degrees from the picture. I don't even have to do any math. It's 3 times 90 degrees. And all radian angles can be found in the same way that we've done these two problems. Start at 0, identify the size of your pizza slice, and then count around. If you don't eat pizza, maybe it's a pie slice. Now, you can, of course, do that for every single problem where you see a radian, build your pizza slice around. At some point, you will start to recognize really familiar radian values and be immediately able to know where they are. Like when I tell you 150 degrees, you probably don't go like, oh, that's a little more than 90. Where is that? You probably think, oh yeah, I've worked with those enough that I know 150 degrees is an angle that looks something like this that I'm making with my hands. And the same thing will happen to you with radians, but I want to help accelerate the process by going through the most famous and common radian values. Like I would say 99.9% of problems use one of the following angles. And there are quite a few, but not so many that it's overwhelming. And they're all based on the building blocks we've made before. So the first set of really important radian angles are the quadrantal angles, or the quadrant angles. So you can imagine, of course, that there is some unit circle sort of sitting here in the plane. Can I center it a little better? Yeah, some unit circle sitting here in the plane. And as we go around, we can list the different radian values. So the first radian value will be 0 radians. That is no change. The next radian value, well, we've already listed this one. It's a half of a half circle, so that's pi over 2 radians. The next radian value is just the full half circle, so that's pi radians. And we did the last one in the last example. That's 3 pi over 2 radians. So when your denominator is 2, you're looking at quadrant angles. And then finally, I guess if you get all the way around, 0 is also the same as 2 pi radians. So those are the most important quadrant radian angles. The reason those are the most important is they are the angles that create the landmark points on our sine graphs. This is not a story about sine graphing, but those are the 4 points, 0, pi over 2, pi, 3 pi over 2, and 2 pi, that when we do graph sine and radians in just a few sections, those are going to be the key values on that graph. That's why I call them the most important, because they relate to that graph. All right. So now I want to think about counting around the circle in quarters. I have done a little bit of a sneak by pre-typing these in, and I'm just going to erase them as we go. So first we start at 0. Then the next radian angle was pi over 4 because it's a quarter of pi. Then after that, we've already seen this as pi over 2, but it's also 2 pi over 4. We have 1 pi over 4, 2 pi over 4s. The next has to be 3 pi over 4. Then we have pi, or 4 pi over 4, counting around 4 slices. Following that, we have from the example we did above, 5 pi over 4. Following that, we should have, we know from the quadrant angles that this is 3 pi over 2, but it's also 6 pi over 4. And then finally, we should have 7 pi over 4, 7 total slices. And then a full circle is both 2 pi, and you can also consider it 8 pi over 4. So any of these angles that have multiple names, just from reducing the fraction, often you'll see them in the simplest version, but I like giving this unreduced circle to show you that radians really are just counting around in a pattern. Same, counting by the same distance each time. So this is the pi over 4's circle, the quarters. Let's look at the pi over 6's and 3's. And I do look at these together, the pi's over 6 and 3, because they are very much related. So we're going to play the same game, erasing as we go. We start at 0. On the pi over 6 chart, the first unit is pi over 6. That is, we took a half circle, cut it into 6 pieces. You have one of those. You probably have 6 of them right here in your hands. If you had 2 of those, you would have 2. Oh, sorry, I went a little ahead. You would have 2 pi over 6, which we also call pi over 3 from reducing the fraction. So that's our first pi over 3 radian around. Then we get to the top quadrant, which is pi over 2. Notice that pi over 2 is not an even multiple of pi over 3. That is, over on the pi over 3 side, pi over 3 goes from the first quadrant right to the second quadrant. It does not hit an even multiple of pi over 3 on the top and bottom quadrants up there. Okay, continuing around. 3 pi over 6, we then have 4 pi over 6, which fractionally reduces to 2 pi over 3. We then have 5 pi over 6, which does not reduce. We have 6 pi over 6, which reduces to pi, and also can be reduced to 3 pi over 3. So if we're counting on the green circle, we have 3 slices. We're counting on the red circle, we now have 6 slices, although they are equivalent slices in angle. Continuing around, we have 7 pi over 6, does not reduce. We have 8 pi over 6. 8 over 6 does reduce to 4 over 3, so that would be 4 pi over 3. Then we have 9 pi over 6. Well, 9 pi over 6 reduces to 3 over 2. 9 6, 3 halves, so that's 3 pi over 2. Does not appear on the green circle, counting by pi over 3's. Then we have 5 pi over 3. I don't know why that one's not in red. That's awkward. Oh, wait, I do know. I lied. It's over here. We have 10 pi over 6, which is equivalent to 5 pi over 3. And on the green circle, it's just 5 pi over 3. Then we should have 11 pi over 6, almost a full circle, not equivalent, no equivalent on the green circle. And then finally, if we're counting by pi's over 6, we should get to the unreduced 12 pi over 6. Well, what's 12 over 6? 2 pi, or 2. Counting around 5 pi over 3, the next is 6 pi over 3. What is 6 over 3 reduced to? 2. So that's also equivalent to 2 pi. So that, my friends, are all the important radian angles you will see and kind of need to eventually get to know. By the end of this unit, you will be so familiar with any and all of these angles. I know it seems like a lot right now. You'll be so familiar with them that if I walk past you in the hallway and I shout 11 pi over 6, you'll be able to put your hands, right in that position exactly that way, because it's going to become really instinctual, just as instinctual as degrees. So again, here they are all in a chart. If I have you in person, I will also have a nice little chart of these for you that I'll probably hand you. One note, often if you search for a unit circle, you see all these circles, all of those 3 circles that I just built together in the same circle. And that actually drives me crazy. You'll see this everywhere in math. And here's why it drives me crazy. These little slices that they've now cut the pizza into do not have equal size, right? We've got one big slice, a 30-degree slice, and then we have like a 15-degree slice. And we have a 15-degree slice, and then we have another 30-degree slice, and it's just a huge dang mess. So yes, you'll see this, and it's a useful thing to memorize, but I actually think it's unhelpful for learning just radians themselves. This is more useful for learning the trig values as you go around. So I would not think you can say, like my advice to you would be not to use this unit circle, but instead to think about the unit circles that are even divisions around the pi over 3 circle, the pi over 6 circle, the pi over 4 circle, and the pi over 2 quadrant circle. Here are some additional things that might happen, complications, when dealing with radians. First, negative radians. So a negative radian angle is treated the same as a negative degree angle in standard position. It opens clockwise instead of counterclockwise. So if I was asked to draw negative 5 pi over 6, I would do as I've been doing. I would start with a 0-degree line, and I would determine the denominator is 6, so I'm thinking about chopping a pi half circle into 6 units, except this time I'm going to do the bottom of this half circle. And then I'm going to shade or count 1, 2, 3, 4, 5 in the negative direction to arrive at the angle negative 5 pi over 6. So that's how we compute negative radian angles. Now, you may immediately be noticing from this picture that there is another way to express this angle as a positive radian angle if I have the same terminal side and I were to just open the other direction, open the positive direction, turning positively, I would have 6 pi over 6 plus one more pi over 6 little slice. So this is equivalent, just from the picture, to 7 pi over 6. And those two angles that have the same terminal side but different numerical values are called coterminal angles. So coterminal angles are angles that have the same, that share a terminal side. In degrees, those things that we no longer speak of, but in degrees you found coterminal angles by doing x degrees plus or minus 360 degrees. That is, plus or minus one full turn around a circle can give you a coterminal angle. In radians, coterminal angles are found by adding or subtracting 2 pi. So we'll have x radians, we'll just do in parentheses, plus or minus 2 pi radians to find coterminal angles. So, for example, in the 5 pi over 6 example, or the negative 5 pi over 6 example, sorry, to find a coterminal, I could add 2 pi to that angle. Now, one nice thing about radians is that it's actually easier than adding degrees. To add 2 pi, I just need to take 2 pi and change it to a version of 2 pi that has a denominator of 6. So 12 pi over 6 is the same as 2 pi, right? That's equal to 2 pi. And negative 5 pi over 6 plus 12 pi over 6 is just the same as doing negative 5 plus 12. And you get 7 pi over 6, which is the answer that we had determined from the picture just above. So coterminal angles in radians are really nice. You could also find a second coterminal by adding 2 pi again. So I could add 12 pi over 6 again, which would represent going one more turn, full turn around the circle counterclockwise, and get 7 plus 12 is 19 pi over 6. And that's another coterminal. So coterminals to negative 5 pi over 6 include 7 pi over 6, 19 pi over 6, and any number of plus or minus 2 pi's. All right, so some other radian trickiness, related, of course, to radians and coterminals, are radians larger than 2 pi. So say I was looking at 17 pi over 3. This is where the approach of drawing it out breaks down, because yes, what I could do is draw a circle and label out the pi over 3's. So that would be taking the top and bottom halves and cutting them into 3 pieces each. So I'd have 6 total pieces. And then counting 1, 2, 3, 4, 5, 6, all the way around until I got to 17. I could do that, but that seems annoying. Let's not do that. So instead, what I'm going to do is reduce this down. So to reduce it, I'm going to subtract 2 pi, or multiples of 2 pi. So let's subtract it by subtracting 2 pi. Well, I don't want to subtract 2 pi. I'd actually would rather have a denominator of 3, so I'll subtract 6 pi over 3. We'll do that one time. 17 minus 6 is 11 pi over 3. So that's a coterminal, right? This is coterminal to this. They would have the same measure. So I could count 11 circles around now. I still don't want to do that, so I'm going to subtract 6 pi over 3 just again. And 11 minus 6 is 5. So 5 pi over 3, that is an angle I could draw. So 17 pi over 3, instead of drawing that, instead I will choose to draw 5 pi over 3. I can draw that just by highlighting 1, 2, 3, 4, 5 of these pi over 3 size segments, and then constructing the angle 5 pi over 3, boop, like so. So that's how we deal with radians larger than 2 pi, is we just take away 2 pi until the radians are smaller than 2 pi. You've done this in degrees. If you've ever seen, 950 degrees, and you tried to figure out how big that is, the move that you will do, you can just do 950 minus 360. Until you get to an angle that you know what to do with. So it's the same idea. We're just replacing that 360 with a 2 pi. Finally, this is actually one of my favorite things, non-standard radian angles. So we've just spent 30 minutes talking about how to do angles where the denominator is 2, 4, 6, 3. We have never done anything where the denominator on a radian angle is 5. So what will we do if the denominator is 5? Well, let's first establish what the denominator means. I can think about this as 13 times some pi over 5. And then pi over 5 is saying, just like we've done with any other fraction of pi, take a half circle, which we've labeled pi, and just slice that into 5 equal pieces. To the best of my artistic ability, I think it would look something like this. 1, 2, nope, that's 1, 2, 3, 4, that's 5, yeah. 4 lines makes 5 pieces. And then I could do the same. I guess I could just continue these lines. One, 2, 3, 4, 5. Yeah. Now, this is interesting. I can look at this, and I know they're not equal size. You have to imagine that they're equal sizes. That's my drawing failures. Here. Yeah, that's a little better. So then, I want to think about what 2 pi would equal in the units of pi over 5. Well, 2 pi, I can see that there's 10 total pi over 5 size slices, so 2 pi would be 10 pi over 5. I notice that 13 pi over 5 is larger than 10 pi over 5, so I need to do 13 pi over 5 minus 2 pi, but I'm not going to take away 2 pi, I'm going to take away 10 pi over 5, and that gives me 3 pi over 5. That is an angle I can find just by going back to this picture, taking my slice size of pi over 5, and shading in 3 of them to make that the terminal side of 3 pi over 5. So that's how you deal with a non-standard radian angle when there's a pi involved, which is just the same procedure with different numbers of slices. The denominator is different, you just draw a different picture. Here is something else that's confusing. What do you do if you have radians, but there's no pi in there? What? Mr. Eck, well, that can't be. That 2, there's no pi there. That obviously must be degrees. Some people think about the pi, I guess, as like the unit symbol for radians. It is not. In fact, before we get into this problem, I want to be really clear that angles from here on out, angles with no symbol are assumed to be in radians. So pi over 4 is in radians, 21 pi over 3 is in radians, 1 is in radians, and 30 is in radians. Angles with degree symbol are in degrees, 12 degrees, 180 degrees, and even 6 pi degrees. So really work on this idea that the pi is not the unit symbol of radians. It actually means something, and a radian can't exist without a pi. So what? How, back to this idea, do I mean by a radian with no pi? So we've been thinking about radians as proportions of the total circumference 2 pi, but technically 1 radian is officially defined as the length of 1 radius. That's why it has that name, by the way. The length of 1 radius, if you take that little segment and wrap that exact length around the edge of the circle, it'll be about this long, approximation, then that is 1 radian. So this would be like an arc of length 1. And this is a situation where a picture is actually worth 1,000 words. So I did not create this diagram, but we are going to take a look, maybe. And I'll post a link in show notes. This is just from the Wikipedia article on radians. But I find that this picture is extremely instructive. So we'll just take a look and let it play a couple times, looking for that definition of radian as 1 radius wrapped around the edge of the circle. Here it goes. So that's 1 radian. 2 radians. That was our problem. 3 radians. Notice how it's not quite to pi yet. There's pi, 3.14. And now you've reached pi. We can finish the circle. That's 2 pi. I'm going to let that go one more time for you to enjoy. And that's how a single 1 radian is related to the other ideas of radians we've been working with. So if this said to draw 2 radians, and there's no pi, right? It's not 2 pi radians, it's just 2 radians. I would figure out what the length of the radius here is. It's 1. And I would figure out what a length of, basically a length of 2 would be wrapped around the edge of the circle. So it looks like 2 lengths 1 and 1 would be right around here. So this angle is approximately 2 radians. Now, fractions of pi, right, fractions of the whole circle have had nice degree equivalents. 1 radian or 2 radians with no pi will not have a nice degree equivalent. I believe 1 radian is around 53 point something degrees. It's not a beautiful equivalent. I think it's actually irrational. I know it's irrational because pi is involved. So we don't usually deal with these integer radians, but they do exist and they can happen. Last item of the day. One of the last items of the day. Converting degrees to radians. This is what you've maybe been waiting for, and I have on purpose been saving it to the end because I really do think it's important for you to immerse in radians and stay and keep your brain in radians as much as you can instead of switching to degrees. But there will be times when you have to convert from degrees to radians or vice versa. So here's how you would do it. There's a lot of different ways you'll see of doing this, about what you multiply by and how you think about it. So I like to approach it with the idea of conversion factors. Remember that your conversion factor, or the best conversion factor, is that pi radians equals 180 degrees. If you know this, you can convert from any degrees to any radians. For example, 13 pi over 3 radians equals how many degrees? Well, I'll make the note that this is radians. Now I'm going to use some dimensional analysis. Let's just multiply by the conversion factor that relates degrees to radians, and I want radians on the bottom. So I'll put pi radians on the bottom and 180 degrees on the top. When we multiply these, the units of radians should reduce out, and we end up with, you can't see that, we end up with 13 times pi. Oh, no. The radians units cancel out, and pi is not the unit of radians, but the pi's do cancel out here, so we end up with 13 times 180 over 3. And I probably could calculate that, but I'll just do 13 times 180 and divide by 3 right here. 780 degrees. So the degrees are coming from right here. We multiplied by 180 degrees, canceled out the unit of radians, so we should have 780 degrees. Say that I wanted to convert 274 degrees to radians. Well, I would need to multiply by something. I'd need to multiply by the conversion factor. That's the reciprocal of the above conversion factor. So I'll multiply by pi radians that are in 180 degrees. The degrees will cancel, and it looks like what I need to do then is just 274 times pi divided by 180, which again you can just do in your calculator. About 4.782 radians. And again, why is this radians? Well, because the conversion factor had radians and it didn't cancel out, while degrees did. Then finally, I said we can now prove that 1 radian has a non-nice degree equivalent. 1 radian times the conversion factor of 180 degrees in pi radians will help us figure out what 1 radian is in degrees. Again, radians should cancel. Now this time there's no pi's to cancel, so 1 radian is just 1 times 180 over pi. 180 over 3 would be 60, so 180 over pi is probably close to that. Now, it's about 57.295, but notice that it's got a pi in that fraction, so this isn't an irrational number, 57.295. And that kind of shows why we don't, start with 1 single radian, is that it doesn't match with a nice number of degrees. Most of our nice radians actually match nicely with degrees. So, converting degrees to radians. If you look online for this, you'll find a lot of different formulas and things to memorize. Don't need them. The only thing you need is normal dimensional analysis and the conversion factor that pi is equal to 180. Finally, and this is for good this time, I want to talk briefly about arc length. That is something that is substantially easier in radians and is one of the neat consequences of radians. So arc length, of course, is something that you've maybe seen in a geometry class. It's basically saying that if you have a circle, boop, of radius r, and you have some central angle, theta, that, in the past it's been in degrees, then the just physical measured length of this arc, length L, can be solved for. And the old way in degrees that you find it is by doing I think the formula goes like this. The length of the arc is theta over 360 times 2 pi r. And how does that formula make sense? Well, at least in degrees, this was the proportion of the circumference, and then this was the actual circumference. In radians, this actually boils down in a really simple way. In radians, the formula for arc length is L equals r times theta, as long as theta is measured in radians. So no weird proportions out of 360 or anything like that. And the reason is that radians already have that proportionality built in. They already contain the information about the proportion of the circle. Let me take the old arc length formula and rearrange it for you one more time. Let's see. So this is saying L is equal to theta times 2 pi over 360 times r, right? Same formula. Well, that's theta times r times pi over 180. Guess what this pi over 180 is basically doing? It's converting theta to radians. So, all of that old arc length proportion formula, it's almost just like sneakily turning it into a proportion. Well, our radians are already proportional. Theta is already in radians representing the fraction of the circle. So the arc length formula in radians, instead of doing a goofy proportion, is just L equals r theta. I will also mention some books use the S for arc length. S equals r theta. The same thing, different letter. So let's use, I want to do a radian proportion problem, and we'll do it in 2 ways. First, I'll do it the old way. So I need the proportion of circle. So this would be pi over 2 I'm finding, the arc length. If a radius is 3 feet, the angle is pi over 2. I'm looking for the length of the arc. So what am I looking for here? Well, I would need to do the radian pi, color code here. The radian pi over 2. But what proportion of that is out of 2 pi? And then I would need to multiply by the circumference, which is 2 times pi times 3. Right, so the proportion of circle times circumference. Well, look at this. Proportion of circle and the 2 pi and their circumference immediately cancel out, and they'll always cancel out. So the old way is just saying do pi over 2 times 3, which is a length of 3 pi over 2. If I use the new arc length formula, I basically skip that first step. I know the new formula is S equals r theta. So the arc length S or L, whatever, is equal to 3 times theta pi over 2, which is 3 pi over 2. Look, same answer, using either the ideas of proportionality, but if you just don't feel like doing proportions that day, then you are free to use S equals r theta. And what I really want to highlight is nowhere did I have to convert to degrees, which is the wrong way to do this problem. A lot of folks will, when they're first starting out and they're feeling a little shaky, they'll reach for that comfortable degree measure. But guess what? Then if you're converting to degrees and then doing a problem and then switching back, you're doing 3 problems when you should be doing 1. That's not where we want to be. I want you to stay in radians and immerse yourself. So in closing, you have now a great deal of power. You can make all kinds of angles with your new radian powers. It's just about putting the pieces together. The first time I did this activity with a class, I cut out my radians, my little paper cutouts that are now on my floor, and I colored them in and taped them together into the picture that looks like this. I would encourage you to do this, hang it on your wall. This is your radian diagram. And also, the next time you go to the pizza place and you want to order some pizza, and you can be exactly as precise as you need to be with the proportion of pizza that you would like to eat. Now it is my lunchtime. Thank you all for watching. I'll see you in class. Goodbye.